Alright, hello and welcome. Here we are again with another problem to look at. This is word break 2 from LeetCode. We'll get right into it. I have some music playing that I'm listening to. I hope that's okay. I don't think you guys can hear it, so it's pretty loud. It's a hymn. Word break 2, let's see how this goes. I feel like I should be doing something. Given a string S in a dictionary strings word dictionary, add spaces in S to construct a sentence where each word is a valid dictionary word. Turn all such possible sentences in any order. Note that the same word in the dictionary may be reused multiple times in the segmentation. So this is very similar to another problem we worked on already. And these words could have different lengths. Okay, cats and dog. Cats and dog. Cats and dogs. Cats and dog. Pineapple, pen-apple. Pineapple, pen-apple. Apple pen. Pine, apple pen, apple. So there's quite a few. Pineapple, pen-apple. Pineapple, pen-apple. Pineapple, pen-apple. Note that you are allowed to reuse a dictionary word. Oh? Wait, really? Oh, if there's a replacement, this is, I know exactly what to do. Cats and dog, cats, dogs, and cat. Alright, so there could be a lot of words in the dictionary. The word's only length 10, S is only length 20. English lowercase letters, all the strings are unique. Alright, so this is what you would call, this is a depth first search question. You really have to brute force this. There's kind of no other way. Yeah, that's kind of it. So this is actually probably one of the easier questions. If you're not familiar with this sort of form of question, though, it could be extremely challenging, I think. So we're going to include a vector and a string, and we don't need to keep playing music. We'll just turn that off. So yeah, I already know the answer to this one. Neither of these need to be. What you're gonna want to do is dump. So here's one way, right? Here's sort of a memoized recursive approach would be to first you dump all your strings in the dictionary into a hash set, unordered set. You also actually don't even need an unordered set. You can use a prefix tree. Also, is slightly more efficient. Nah, it doesn't really matter. It doesn't really matter, I think. Yeah, you could use a prefix tree, or you could just try, or you can just use an unordered set of the strings. I'm just thinking it's more efficient to use a try. I think it's more memory efficient to use a try, probably, but it really doesn't matter. So we won't do too well on the memory on this one. But building a try is kind of annoying because you need like try nodes, and there's like an algorithm to, not an algorithm, but like a way to actually process the try to get each string. But the basic algorithm is going to be the following. You can use a try or an unordered set to do this. So we're going to use this, we'll just say this set because it's simpler. Dump all the words in your dictionary into this unordered set, and what you're going to do is left to right, you're going to build a string, and the recursion is going to be something like the following. The string you build, if it's in the dictionary, then that begins a whole sequence of, basically you would recurse from that point, and you'd recurse from that point, and you would the resulting set you get of strings. And we can do a vector of strings. I think it's better to do, we'll join them at the end. You have a vector of strings from the recursion. You would append this to the beginning of that of that vector of each of those vectors. So maybe a stack is better. We can do a vector of stacks of strings is probably better. So we can push this into on the top of the stack, and then later we could pop down the whole stack. So it's a vector of stacks of strings, and it's a vector of stacks of strings. Yeah, excuse me. And each of those stacks in that vector, you're going to push this string that you found onto them. And that's pretty much it. You do that recursively. You can also do this using dynamic programming. This is what I want to try to do now, which I try to get some practice with dynamic programming. What you would do is, so this is going to be for each character, some value I. So the recursion itself, you would say there's an integer index, which is the character you're looking at the moment, and then you have if what you're looking at. So actually, you have two variables. You have the starting point and the ending point for the string. That's the key. And you could take the substring, but you could also just build the string too. That's a little bit easier, I think. And this is actually very similar. Actually, this is very similar to a problem that we just did with the palindromic strings. We can go backwards from right to left, and you can add. Now, it doesn't need to be a stack if we're going right to left. It could actually be a queue, I think. If we're going depth first search, if we're going from left, if we're going top down, we would put it into a stack. If we're going bottom up, we could put it in a queue. Put it into a queue, and you would say something like the following. So the initial state is going to be, so it's actually very similar to what we just did with the palindromes. So you can have an outer loop that's your starting index. An inner loop is the size of the word, how many characters. And in the inner loop, we're going to build the string, right? Check this, and then the condition that we're going to do is if this string is in our unordered set of our dictionary words, then what we can do is we can take dp of our index plus 1, and that should return a vector of queues of strings. And for each of those, we're going to add this string to those queues. Basically copy that whole thing and copy that into this DP slot. And we DP from right to left. We do it that way. And then we take DP of 0. A tricky thing here is, excuse me, wondering if we have too much memory if we do it this way. I don't think so, because so what's interesting here is we don't necessarily need to memorize anything for this recursion. I don't think we actually need to use any memory beyond what we're passing from function to function, which is really interesting. That's kind of what makes this the depth first search is actually a little bit better in terms of memory. We actually don't even need the, maybe we do. I'm sorry, no, the depth first search, no, I think we do need some memory, because the tricky part, the only issue I'm having with the depth first search is that you have index I, index j, you do have to loop over like j from all the way to the end, for wherever I is to the end. And you could still recurse, that's fine. If you don't memoize, though, then you'll end up doing a lot of redundant work. I think that's part of the problem. Yeah, that's a lot of recursion. Yeah, you have to memoize. Yeah, if you don't memoize that, then what happens is all those recursive calls become. Okay, I see. Yeah. You have to combine. You have to combine all of those recursive calls at the end, all those results. But yeah, so I mean, you're only going to use whatever the final memory that's required to store. You're just going to really just double that, I think, as a total memory for all of the sub parts. Not really that much extra memory you're using, but I guess what I'm trying to say is how are we doing on time, by the way? I think the DP that I just described will work, but one issue is like, what does the memoized version look like? I think you do need to memoize, because if you don't memoize, then you're performing like an inordinate amount of. I think it becomes exponential, like the number of redundant function calls that you're making. It becomes quadratic if you do memoize. Yeah, all right, we'll do the DP. So it looks like the following. Call initial value. We're going to say DP. And what DP is going to give you is vector string q. It's going to be a vector of q's of strings, which you don't see too often. Q vector, and it's going to be an array of vectors of q's of strings, and the number is going to be n of these, and we're going to say initial value for int I equals 0, I is less than n, plus plus I. These should all just be dp of I. We're actually going to do plus 1 as well. And we're going to say all of these are just vectors of q's of strings. Maybe I should name this something. And they're going to have nothing in them. Actually, these should be kind of uninitialized. You could do this too. I mean, just I don't know. I actually don't know what these should be initialized to. I know what the one all the way on the right should be initialized to. I have an idea what that might be. What that should be initialized to. Effectively an empty queue. So this we could type def also, I think. Type def this to VQS or something. Vector queue of strings. I don't know. VQS. I don't know. Vec of strings. I don't know. We just call it VQS. I'm not sure what to call it. A vector of q of strings. Okay. So this is initially we're going to have a vector which has no queues in it. Could be one queue that's empty. So what's going to happen is you find a word. You're going to copy the whole vector of all the queues that you have, all of them. Yeah, what you have. You find that word, copy this, and then in each of those vectors, or each of those queues, you're going to push this string. Yeah, and you're going to combine all of those to create. Yeah, you're going to add each of those vectors, each of those queues, and each of those vectors to a larger vector of queues. Yeah, that's how it works. You're going to combine them. That's interesting. So VQS of, then we're going to have a standard queue of strings, and we're going to just have one. We're going to actually do something like this. So these really could just be empty. Actually, they really don't need to be anything. You could say it's just an empty vector. Yeah, so maybe I can do this, something like that. So there's just an empty vector altogether. And then here we're going to have one empty queue. That's it, of strings. Yeah. Okay, anyway, so now the DP is going to look like the following. So we're going to say 2 loops, going back to front. So this loop is going to be int k equals 1, k is less than, should be n, or n less than or equal to n, increment k. And we're going to go from the back to the front, so n minus 1, or I equals n minus 1. And I is greater than or equal to 0. Increment I, or decrement I. We're going to say we have a string, standard string s. So now this string, we're going to build the string right to left. That's kind of tricky because we want to append to the left side of the string. Now, can we do that easily? I don't know. I think appending to the right side of the string is relatively easy. I don't know if concatenating on the left side is less efficient at all. In that case, maybe we do want to try to use stacks. We could go in the other direction too, if it's easier. I think it might be easier actually go left to right rather than right to left, because I think concatenating on the left side of a string is probably less efficient than concatenating on the right side. Is that? I don't actually know. I don't actually know. Could be totally wrong about that. Could reverse the string every time. No, that's not good. Let's do left to right then. So actually, if we do left to right, then actually we should make the array at the 0 index. We would make it. It would be stacks instead of queues, and it would go left to right. And you would say, once you see a word, take everything to the left of that word. Yeah, you'd still have the same idea. You have a starting index where the word is that you're going to grab, and then you would update the next index with that word. Interesting. How does that work? It'd be like dp of k is going to be whatever the previous index was that we're at. So I. Now what's tricky about that is You might want to have the initial value to the left, and so you kind of move everything to the right a bit, which is a little bit confusing. So for instance, if I starts off at 1, that's where the string starts. Oh, I have to think about that. So if I still go left to right then, instead of right to left, because you can, it's just you have to reverse things and use stacks instead of queues. The first word we see, we want to put it on a stack. The stack that we're going to put that onto is what? These are all the stacks of one word. Which it would copy from a previous position. Would it be position 0? Would that just be immediately? See, the thing is, position 0 could have a word there. That's the thing. I guess the index you're at is everything to the left, not including that index. So dp of 0 would be empty. dp of 1, yeah, okay, that works. That's fine. We could do it that way. We could just same deal, except everything is empty except for everything's empty except for the first value. We could use stacks instead of queues. There we go. Let's do it that way. And we'll just call this VSS then. Vector of stacks of strings. Okay. A little bit better. Not better, but we could do it this way instead. So now we're using a lot of time here. 20 minutes? I think, yeah, it was a lot more than 5 to 10 minutes, but that's okay. I think we'll still be able to do this relatively quickly. So now we are going to go from 0 to n plus I, return at the end, return, we'll process return value. Result. Excuse me, we'll get to that in a moment. S is going to start out as an empty string. We're going to take k. For each k, we're going to say s plus equals I guess minus k, s of I minus k, or plus k minus 1, something like that. We'll call this t instead of s. Temp string. Yeah, I mean, yeah, that's fine. That makes sense. That makes sense. So in k is n, it's just s I minus 1. Oh, this is going to be I plus k minus 1 is less than n. That's or alternatively, it's less than or equal to n. I plus k is less than or equal to n. I kind of prefer to write it this way, so it's clear what's happening. So you have t. You say if, and we're going to dump into an unordered set. We said. dp prepare set of dictionary words for dp for the dp for const standard string reference word w and word dictionary. We're going to use standard unordered set of strings of we'll just call them words ws. So ws.insert w, and then we can say if w.count ws count of t, and then do the following. Say dp of, now we said I plus k. I think it's going to be, yeah, I plus k makes sense. That is going to be the following. We're going to have a reference. So auto reference of target. It's going to be dp of I plus k. That's our target. And we're going to say for each value in dp, so we're going to say auto reference x in dp of I, right? We're going to say, and it's actually going to be, it's not going to be a reference. It's actually going to be x is going to be a copy. We're going to copy each of the stacks in dp of I. We're going to say x dot push t, and then target dot append x, right? So this is kind of the subtle thing, but x is going to be the stacks of strings in dp of I, each of those stacks, and we're going to take each of those. We're going to append t to that stack, and then we're going to append that stack to our target, which is dp of I plus k. Yeah, which is actually just going to be this then. Well, actually, it's a little bit more efficient to make a reference to it first, so we don't need to access it over and over in the loop. Now, what we can do is go to the end here, process final result. So what should happen is dp of n, or dp of n should have our result. We're going to say auto console reference, or yeah, of result is going to be dp of n. And we're going to say we have a result, which is the vector of strings. Or return value. I'm going to say for each in this result, for each x in the result, it's going to be the VQS, for each VQS, a vector of stacks of strings, or just for each stack of strings x in the result, we're going to say string t is equal to an empty string. We're going to combine, we're going to pop everything off the stack. Say while not x is empty, say t plus equals x dot top. And really it should be x dot pop. I think when you pop it, it returns the value. We'll find out shortly. And it's not just pop, it's going to be, I want to say the first value we could pop, and then every value after that, we would add a separator delimiter. That's what they have over here. With a single space. Okay. How are we doing on time? All right, 30 minutes. Yeah, this is a little bit more involved than I thought. This is not too bad, though, I think, this question overall. But yeah, we want to have a space except for the first. So that's the only key thing here. We can say we'll add a space if x is not empty. Could do it that way. So if it's not empty, we're going to prepare for the next thing and add a space. But if it's empty, we don't add a space. And now each t is going to be added to return value, append or push back. It's not append, append is in Python. And vectors is push back. and then we return ret. Okay, kind of involved. We could maybe split these into pieces, but we'll go from here. See how we do. Alrighty, no matching conversion, functional style cast. Oh, I did this wrong. There's one of these, and that's what it's going to be. An empty stack, one empty stack. Undeclared, oh, x.pop. Some compiler errors. There's always something I missed. Grateful for compilers. Pop has type const.o. Excuse me. Excuse me. Didn't even realize we are going to modify these stacks. What? Where did we get const from here? X reference, it's not const. What's the issue? This argument to member function pop has type const stack string. No. No, it doesn't. No. Okay. We have VSS of DP. Result. Oh, that's. Result is const. Got it. I missed that. That's my mistake. Not sure why I did that. No viable overloaded T. Really? It should be a string. Does pop not do what I think it does? Oops. Let's try again. Let's try again. Pop. Void. Okay. Fair enough. Yeah, it's okay. Anyway, that's interesting. That is the problem with that is in Python, I think the pop will actually return the value. Some of the languages, pop will actually give you the value. In C++, that's not the case. So we're really close here. We have dog, sand, cat, dog and cats, cat, sand, dog. So it looks like we're just reversed. It looks like we are supposed to use a queue, not a stack. Whoops. I don't know how that happened. I don't know how that happened. Whoops. In that case, by the way, we probably don't even need a the queues. We're going to use the queues anyway, but we're going to use the queues anyway, but I suspect we didn't actually need to use queues. Or didn't need to use stacks. I don't know why I thought we needed to use stacks. This should be front. Does this still work? Does it compile? Oh, there we go. Okay, nice. Probably that's it, you know. How do we do? Almost 35 minutes. Yeah, almost 40 minutes. Okay. All right. You know, I would like to be able to solve these problems faster, but whatever. If you're slow, you're slow. What can you do? I think we got it. We're gonna give it a shot. Let's see how it goes. Hey, there we go. Oh wow. 0 milliseconds, 100%. Sweet. A lot of memory though. I don't know how you could do this not using so much memory, quite frankly. I guess you could, instead of DP, you could like depth first search, something like that. I'm not entirely sure, but obviously this is super fast, so yeah, not bad. All right, we'll move on. I don't know, there's probably a way to reduce memory usage. Excuse me. I don't know. Let's think for a moment. I mean, I don't know, man. I think maybe you could swap these loops and optimize. Maybe that's something you do. Can you? You could put K on the inside, K on the inside, I on the outside. Or K on the inside, I on the inside, and K on the outside. Or how long the strings are going to be. I don't think so. I don't think that, because you have to build the strings as you go. I don't know, man. Seems... You could, it's definitely less memory to use a try. I mean, there's that. It's a lot less memory to use a try to perform the same thing, presumably. Not always, though. I mean, the try could be the same amount of memory. It's not always better. And then I'm thinking that DP is the issue, but I really don't see how, like, the problem with not using a DP is that you end up doing a lot of extra operations if you don't use the DP. That's the issue. Like you could do the same thing with like repeated calculations without using the DP. And I guess you wouldn't use as much memory, sort of, because a lot of different paths wouldn't produce anything, something like that. I don't know. I'm not really sure. There's definitely a lot of duplicated memory, I think, for the use cases they gave. But in asymptotically speaking, I don't think you really use more memory than you would otherwise. So that's kind of interesting. So here's a case where the DP is a lot faster. I think you could write a I don't know. I think you still have to memoize anyway. Like I don't see how you could do this without memoization. It wouldn't be efficient enough. I think something like that. I don't know. Some people figure maybe there's a way that I'm missing here. We could check the discussion, but I'm going to leave it for now. There's some way to optimize the memory here, but I don't know it offhand. But yeah, that's pretty good. So how are we doing? Yeah, 40 minutes, not too bad. Thank you for watching. That was good. I guess we'll end here. I don't know. Should I take a break again? Maybe I can. Maybe I should. Kind of want to like lay down. These problems are hard, man. They're challenging. They kind of take a lot out of me. Like I said, I'm trying to get to a point where I could solve like, I don't know, like a boatload of these in an hour, and then I could solve so many of them in an hour, then I could do and then I could do, if I could do many of them in an hour, then I could do many of them per day, and then try to solve like all of them on the website in like a month or two, something like just do it really fast. So that's the goal, but I don't know. We'll go slow. All right, thanks again for watching. Talk to you soon. Take care.